Okay, today we're discussing the concept of latent heat. Latent heat means basically hidden heat. If you were to plot a graph showing the warming of an ice cube or a block of ice, say it was a block of ice at -50, you would follow this kind of pattern where you would see the ice would go from a sub-zero temperature till the melting point of water. At the melting point, the ice would begin to melt, but it would stay at the same temperature, 0 degrees Celsius, until all the ice was finished melting. And that's called the latent heat because heat is being applied to the breaking of the bonds that form the ice. So energy is going into doing that, but it doesn't warm up. The energy whatever energy ice cube absorbs at 0 degrees Celsius goes into breaking the bonds and turning the solid water into liquid water. So they call it latent heat because the effects of it appear to not be doing anything. They're hidden. The actual result is that it's breaking the bonds and fusing the ice. Once the water has finished melting into the liquid and turning into liquid, once the ice turns into liquid, the liquid water begins to warm up. And it'll follow that pattern until it hits 100 degrees Celsius, at which point it'll begin to boil. Once the water begins to boil, again, it'll stop changing temperature until all the water present has been turned into steam to get into the gaseous phase. And again, that's called the latent heat of vaporization. The amount of energy needed to be put in for that phase change to take place is called the latent heat vaporization. Once the water has turned into a gas, then you can start warming up the gaseous phase as well. And each one of these steps has its own either specific heat capacity or latent heat. We'll see that in truth the specific heat capacity of ice varies with temperature. And this value was what I looked up in the CRC and is accurate for water, ice, at -30 degrees Celsius. And it changes moderately around, for around 10 degrees plus or minus, it remains around that value. If you really wanted to do an accurate calculation of how much energy it takes to melt something from -50 and then get to the point where it's steam, you would have to use a complex formula to input all the various values of specific heat capacity related to temperature. You'd probably be forced to use calculus to do the calculation accurately. However, for our purposes, we could probably use these values and get away with it because we're pretty close to zero and we don't have to have a super accurate value. And it serves to drive home the idea that at each juncture there's an expenditure of energy. So we call this the specific heat capacity of solid water, the latent heat of fusion, the specific heat capacity of liquid water, and finally the latent heat of vaporization. Each one is attended by an energy change. So if you wanted to calculate, for example, how much energy would it take to change 1 kilogram of ice at -20 degrees Celsius into 1 kilogram of steam at 100 degrees Celsius, you would have to perform 4 calculations. The first calculation would involve the warming of the ice from -20 to 0. Then you would do a calculation to find out the input of heat to go from 0 degrees, to stay at 0 degrees and to turn the ice from solid to liquid. Then finally to warm up the water from 0 to 100 degrees Celsius. And lastly to undergo the phase change at 100 degrees Celsius to boil the water from the H2O liquid to H2O gas. So 4 separate calculations, and then you total up all the values. For this particular calculation, the final answer we worked out was 3.52 times 10 to the 4 joules for this part, 3.33 times 10 to the 5 joules for the second part, 4.184 times 10 to the 5 joules for the third, 2.258 times 10 to the 6th for the last, and the total was 3.04 times 10 to the 6 joules. So about 3 million joules of energy. And you'll notice that by far the largest amount of energy that's expended is expended in getting the water to go from the liquid phase to the gas phase at 100 degrees Celsius. The conversion of water into steam requires a large input of energy.